All right, welcome back. We are in chapter 8.3 of our book, which is talking about volume. And we're going to be talking about five different ways to calculate volume. Or let me rephrase that five different scenarios. The strategy is going to be very similar on all the ways. But let's start by talking about the most basic. And looking at the diagram that we have here, the most basic says that I've got a function, y equals f of x, and I'm going to rotate this around the x-axis. And when I do it, it's going to create a solid. And you can see off to the side, there's a three-dimensional rendering of what that solid might look like. And the question is, what's the volume of that solid? So let's think about what we know. If I take some tiny thin sliver, and you may, well, you hopefully remember that in the last section of the book, we talked about finding the area of that sliver. But instead calculating the area, I'm going to spin that sliver around the x-axis. Well, what I get when I spin that sliver around the x-axis is I get a disk. And this disk is very thin. It has width delta x. It has some radius r, and you may remember that the volume of a cylinder is the area of the base of the cylinder, in this case circular, so pi r squared, times the height of the cylinder, which in this case, delta x. Well, what do we know about r? Well, in this case, r is equal to the value of my function at that value of x, which means that the volume of a single slice is equal to pi times the function squared times the thickness of my slice. Now, skipping ahead through all the, hey, let's take the sum of all the slices. Whoops, slice. Nope. Slice. The sum of all the slices, we've got a Riemann sum, which we can jump straight up to rewriting as an integral of pi f of x squared dx. We know that we can pull the pi out front if it's convenient for us, or we can leave it in if it doesn't matter. But what we've got now is that the volume of this shape that we have off to the right is just the integral of this circular rotation, starting at the left and going to the right. So let's do a quick example. Let's look at the function f of x equals 2 plus x cosine of x. And to be honest, it doesn't really matter what it looks like, but let's take a quick look anyway, because in the future, different kinds of problems, it may end up mattering what they look like. We've got something that looks like that. And when I rotate it, of course, here's my discs with radius 2 plus x cosine of x. So I'm just going to go straight to the volume of my cylinder is pi r squared delta x. And I really like to write this down every single time. And the big mistake I see is people are so used to calculating area, which is just integrating f of x, that they forget that we're dealing with volume here, and they leave off the squared. And they remember, oh, well, there was a pi in there, so then you get pi f of x dx, which of course is not in fact the volume. It's just the area multiplied by pi, which doesn't help us at all. So continuing, we've got the integral from -2 to +2 of pi 2 plus x cosine of x squared dx. Honestly, in this one case, we don't know a way to find the antiderivative of x cosine of x, let alone plugging it inside of a squared. So we're just going to use the numerical integration feature on our calculator. And what we get is that this volume is approximately 52.43 cubic units. So whatever our units are, the shape that we had in the previous problem right here has a volume of approximately 52.43 of those cubic units. All right. So, my students, go ahead and jump into the textbook and do exercise 7. And when we come back, the second video is going to talk about something called washers. We'll look forward to seeing you then. Thanks for watching.